This video is intended to show you how to use the flow routing spreadsheet, Excel spreadsheet that's been created for routing flow through a wetland, event-driven wetland, and also routing or calculating the treatment of a constituent that is added to the wetland through either a base flow that's coming into the wetland as well as surface runoff that's generated from the watershed contributing to the wetland. You'll find this is associated with assignment number 4, so if you go down to the section on event-driven wetlands, you'll find assignment 4 there, the folder for assignment 4. And if you open that, you'll find the statement for assignment 4, which includes both the it's two problems. One has to do with the flow routing and chemical routing through a wetland, and then and designing that wetland so that it would meet certain standards for the outflow, and then also and chemical output. But then also the second problem has to do with taking tracer data and determining the hydraulic characteristics of the wetland from the tracer. So there are actually two spreadsheets that you'll be learning how to use. One would be the one that's listed here as assignment 4 model for students, and the other one is mixed reactors tracer fitting tool for students. Both of those will be used along with the reference information that's given here in a data file called sav-2 wetland.txt. So for right now, I'm going to show you how to use the spreadsheet called assignment 4 wetland. First, I'll open up the assignment and we'll look at that. This assignment is due April 6th, so it's a little over a week from Monday. You do not have to do any development of any spreadsheets or anything. You just need to use a spreadsheet. In previous years, I've actually had the students go through and develop a spreadsheet, which takes a considerable amount of time. So here you get the advantage of using a spreadsheet that's already been created. So you're asked here to design a constructed wetland to be used for stormwater control, for runoff attenuation, and water quality impairment reduction. The location is Gainesville, Florida. The wetland should be rectangular in shape, with 3-to-1 side slopes. The length to width ratio should be no greater than 3.0. The area limitation is 2,000 square meters. So elevation of the site is 50 meters. That information is used for calculating evapotranspiration, as you'll see later. There's a base point inflow to the wetland of 70 cubic meters per day. The bottom slope of the wetland should be it should be 0.001 meters per meter. We'll assume the velocity equation, mean velocity equation for the wetland is given by the one we talked about before, where the mean depth is used and the slope of the wetland is used, along with the conveyance coefficient alpha, which is dependent on the type of vegetation. In here, where you've got a heavy growth of Phragmites australis, and that here I'm just estimating what the conveyance coefficient is, and I chose 1 × 10⁷ based on recommendations from Cadlick and Wallace. The outflow weir that's controlling this structure is given by this equation. Parameters in this are B1 and then the elevation of the crest of the weir. I'm not going to give you the option of choosing the value of B1. You could do it in the spreadsheet, and but I'm not asking you to do that. And I'm not asking you to change or to choose the crest of the weir, the elevation of the crest of the weir. Both of those are fixed. Those are two things that parameters that could be varied though in the design. The assumed saturated hydraulic conductivity of the bottom of the wetland to calculate leakage out of the wetland is 0.001 meters per day. The watershed contributing area is 5 hectares, and the curve number for that is assumed to be 89. And the water table is at the depth of 5 meters, and being so deep, it actually means that there will be no interference of the water table with the seepage coming out of the wetland, leaking vertically downward from the wetland, from the bottom of the wetland. For the evapotranspiration coefficients, Cadillac and Wallace give crop coefficients, KC, for wetlands. You find that in chapter 4. And you would basically multiply the reference ET times that value of KC. This is all built into the spreadsheet, but you'll need to provide the value of the crop coefficient. There are two other coefficients, CN and C sub D, C sub N and C sub D, which are in the equations for calculating the reference evapotranspiration. One of the files given here on the in that folder is the ASAE standard for reference ET, and you can use that to come up with the actual values of the CN and C sub D. The concentration of phosphorus in the input, the point source, is 4 milligram per liter, and the concentration of phosphorus and surface runoff from the non-point source non-point source contributing area is given by an equation where 0.05 is the coefficient. So whatever the discharge is from the watershed, that discharge in cubic meters per day multiplied by 0.05 would give the phosphorus concentration coming into the wetland in milligrams per liter. The reaction coefficient that determines the attenuation of phosphorus or elimination of phosphorus within the wetland is given by 0.05. This is the area reaction coefficient. Remember, the area reaction coefficient is just the normal reaction coefficient, which has units of 1 over time, or 1 over day, multiplied by the depth. And so this value is 0.05 meters per day. The porosity of wetland is assumed to be 0.85. So here I'm asking you to design the dimension of the wetland, that is the length, width, and depth, so that the peak inflow is reduced by at least 50% and the phosphorus removal efficiency is at least 75%. Both of these numbers are calculated by the spreadsheet, so the calculations are fairly straightforward. I am going to ask you, though, to verify calculations that the spreadsheet does on one particular day in item number 4. Ask you to do that for day number 173. So you'd have to go through and calculate some of the details, but only for that one day, to verify the numbers that the spreadsheet is given. That'll give you an opportunity to prove to yourself that you know how to use the equations. In your report, of course, you'll apply this spreadsheet, you'll do the calculations, change the length and width and so forth within the constraints that are given, so that you do reduce this peak, the maximum peak, by 50%, at least 50%, the removal efficiency overall for the entire period of the record, which is a 1-year period, of that the removal efficiency is 75%. I asked you to do the checking of the details. The details are these things right here on day 173. So the model will report the values, and you just have to go through and make sure that the water balance components, the precipitation volume input, all those things, that you know where they're coming from in the calculations. It should be fairly straightforward for you to see how that is done, but I expect you to go through the details and write down the equations that are being used and illustrate the calculation to show that it does, that the numbers that the spreadsheet is getting, that you can reproduce those. I also expect you to report plots that are given by the spreadsheet, and those plots are listed here, the ones I expect you to use. For that day 173, some of the calculations, some helpful points about how to do those, the ET calculation as well as the runoff calculation from the watershed, which uses the curve number method. Those are, there's an explanation given here of how that's all done. All right, so let's look at the spreadsheet for this first part, and then we'll do a separate video to look at the spreadsheet that's being used for doing the tracer analysis. So going back to the website, we have this one here, the Excel spreadsheet assignment 4 model for students. This is the one that has to do with the routing of the flow. We open that. You won't get a warning like that on your computer, I'm sure. I have something that's messed up about my computer. There are 2 tabs here at the bottom. One is for flow and chemical modeling, and the other one is for meteorological data and calculations. The meteorological data is given here for 1 year, 365 days for the year 1980 in Gainesville, Florida. So we're only doing the simulation or calculations for 1 year. Given here are the day, precipitation, duration of precip, peak intensity, or the hour when the peak intensity occurred, the actual value of the peak intensity in millimeters per hour, the maximum temperature, minimum temperature, radiation, wind speed, wind direction, dew point temperature, vapor pressure based on the dew point temperature, and then a bunch of numbers for the net radiation. And equations for doing these are given in that handout, well, both in my notes, the slides on event-driven wetlands, but also in that document, ASCE standard for calculating evapotranspiration. So you'll have to look through those to see the calculations being done. T-bar is just the average of the maximum and minimum temperature on any particular day. From this weather data, we calculate the potential evapotranspiration, which is what ETO is. So a bunch of these things, I mean, this is all provided to you already. The ETO value would be changed if we were to change any of the some of these numbers that are over here. It also change if we change the elevation of the watershed or the area, the absolute pressure, the total pressure at that location. The value of CN and C sub D are already given here. These are out of that ASCE standards document. So you don't actually even have to fill that in. That's already given. But you'll need to, of course, reproduce the value on day 173, as I've already mentioned. This evapotranspiration data, for the potential evapotranspiration, the daily precipitation that occurs, that information is read then into the spreadsheet that does the water balance for the wetland. So going to that tab for flow and chemical modeling, we have here in that tab things that are calculated by the spreadsheet. And the only thing that you need to modify in here are these things that are in blue. Inputs are in this color. So these cells that you see are the ones that you need to feed information into. I guess I wouldn't change the depth, the head increment for the wetland. That I don't know why I keep getting this error from Windows, but the head increment is just used in constructing this storage discharge table for the wetland. So you can see that these go up by 1/10 of a meter in each. What we have over here is elevation of water or depth of water in the wetland, the discharge that would occur over the weir at the outlet, the area of the wetland, and the volume of the water in the wetland for each of those depths. It then calculates a variable V, volume, divided by delta T plus Q divided by 2. So it takes the V value, divides it by delta T, and then it adds to that this Q value here divided by 2. The delta T is the time step. I have not made that something that you would change. I've assumed here that the time step would be a 1-day time step. Okay. So this table is created automatically for you when you change any of the parameters here in these tables. So for instance, if the B1 is changed, I gave it a value of 200. Here it has a value of 100, but if I were to change that, if you look at the table on the left hand side, you would see that the Q values are going to change. These values are going to change, and also this V over D plus Q over 2 is going to change because the Q values change. So as soon as I change that, you'll note that these values for the Q changed in the column, and also this column E, the values changed. So I'll just change that back to 100. You're going to use a value of 200 there. The weir crest, I have 0.25 meters here. You would change it to 0.6 meters in your assignment. So if I change that to 0.6, you'll see that the H values will change, the Q values will change, the A values will change, and the V values will change. So just by changing that weir crest elevation, you do change the storage routing table. I'll change that again back to 0.25. The wetland length and width are the two parameters you're going to try to design with to meet the requirements. The slope of the wetland is 0.001 in the assignment. The side slope of the wetland that's being constructed, the side slope is 3:1, and that's what value is being given. The alpha value is 1 times 10 to the 7. We got 5 right there right now. The relationship between the discharge going into the wetland from the non-point source area from the watershed catchment and the concentration of chemical in that, the phosphorus in this case, is 0.05. That was specified. The kinetic reaction coefficient K was set to be equal to 0.05. I have 0 there right now, but if I change that to 0.05, and then the watershed area is 5 hectares, which would be 50,000 square meters. Curve number was set to 89. The chemical and the precipitation, the phosphorus and precipitation, is assumed to be 0. The concentration or the base flow discharge is 70, and the chemical in the base flow is 4 milligram per liter. And then saturated conductivity was 0.001. And then you need to look up what this ET coefficient is. Let's say if I use a value of 2. Alright, so doing that, we get some output down here. Everything is calculated nice and automatically for you. And the important ones here, there are mass balance errors that are calculated by the model. So the water balance error, the inflow minus the outflow, the part that's not accounted for in the calculation just because of a numerical error, is less than 0.1%. It's 0.033%. The mass balance error for the chemical is less than 0.1% as well. So these calculations are pretty accurate. The removal efficiency, which is what I'm asking you to design for as far as the chemical removal efficiency, I said it should be at least 75%. For the current design, it's 32.5, which is too low. So what I would do is I would mess around with the wetland length and width. Remember, you want to keep it at a 3:1 side slope, or 3:1 ratio. So let's say if I make this 90 and 30, we should see a improvement in the efficiency, and we went from 32 to 53. So we're approaching the point where we'll achieve that condition. You'll find that it's easy to meet the flow attenuation, that is, reduction of peak flows, much easier than it is to meet the attenuation of the chemicals. The reduction of chemical is a little bit more difficult to meet. A graph showing the inflow and outflow concentrations of chemical is shown here for the current conditions. The blue is the inflow concentration of the chemical, the red is the outflow concentration. And then over to the right of this, there are a bunch of other graphs. So this first graph on the top is a relationship between, actually this is incorrect. It should not be time in days. This should be elevation on the horizontal axis. I'll have to change that in the spreadsheet. And then the vertical axis has got either discharge, surface area, or volume of the wetland. So the discharge versus elevation relationship is given by this blue line. The volume versus elevation relationship for the wetlands is given by the green line, and the wetland surface area versus elevation relationship is given by the red line. Note that we have a log scale on the vertical axis. The graph below that is the discharge inflow, which is in blue, and the outflow, which is in red. We can see that the peak flows, maximum peak flow here is almost 2,000 cubic meters per day. This one's about, what, 1,750. We can see that there's a big reduction because of the storage of water in the wetland. So the wetland is being very effective at reducing the peak flow of the from these, that is generated by these storms. The water depth in the wetland is not uniform. The blue line is the water depth at the outlet of the wetland, at the weir, and the red line is the water depth at the inlet. The water depth calculations are conducted by an analysis that's shown here in this brown area, or tannish area on the right. Listed here are locations along the wetland. The inlet is the left-hand side, and the outlet is on the right-hand side. The location for the at each of these points, remember we have a 90, I changed the length to 90 meters. This would be at the inlet, 0 meters, outlet is at 90 meters. The elevation of the bottom of the wetland is 0 at the outlet, and it's with that slope that I gave, it's 0.18 meters at the inlet. The numbers here in the tan or brown area is the actual water depth. So at the outlet, the water depth on the first day, as these are listed by day, so each row here represents one day. So there's day 1, day 2, day 3, and so forth. The water depth is 0.25 on the first day. At the weir, 0.316, 0.405, 0.431. That's assuming here that the crest of the weir is at 0.25 meters. And we can see that the depth is not uniform. It's 0.25. It's 0.316, for instance, on day 2. It's 0.136 on at the upper end on the same day. This was calculated using a procedure that's explained in the slides, and it's a procedure that basically calculates a head loss in the wetland, accounts for the fact that the wetland is not horizontal, that it's got a slope to it. On the left-hand side for each of those days, we have the head loss given in each of these cells in meters. So you can see the head losses are pretty small, at least there initially. Maximum value should be somewhere around day 173. That's part of the reason why I chose that day as one for you to check the calculations upon. Day 173 is right in here. So there the head loss is about 0.0004 meters. It looks like it's really large over here, right towards the beginning of the simulation, but that's just because things are getting started up. All right, and then so we have a plot of the head loss versus time, and then the last thing here is the hydraulic residence time, or not the last thing, but one of the last is hydraulic residence time versus time. And we can see large variations of hydraulic residence time. When the wetland empties out, evaporation occurs and no big inflows are coming in, the hydraulic residence time gets to be very large. Whereas when we get some of the big inflows, this would be about day 173. When we get those big inflows, hydraulic residence time gets reduced. Well, it's at times like this, when the hydraulic residence time is small, that the treatment of the phosphorus gets reduced drastically, so it becomes less efficient in its treatment. Whereas when the hydraulic residence time is very large, a lot of the phosphorus will be removed because there's more time for that to occur. A plot of the wetland surface area is also shown here. And I can see that I got the wrong plot here too, the wrong axis. I'll have to fix that, but this should be the surface area of the wetland in square meters, and this is time in days. And so we can see that when we have big flows occurring, the surface area goes up, and when we got small flows, the surface area is decreasing. Okay, so I got a couple of graphs I need to fix the labels on the axis. The whole procedure for doing the flow routing is given here in this table. The flow routing table basically takes the inflow and routes the outflow. The procedures for doing that flow routing are explained in detail with examples in one of the documents that's on the website. It's not in that folder for the assignment, but it's one of the separate documents that's along with the slides on event-driven wetlands. And then the chemical routing is given here in the next section next to that flow routing. This would be the chemical routing section. It says chemistry. And here the concentration inflowing into the wetland is given in column AE. The model calculates the flow through the flow routing procedure within the wetland, takes the inflow concentration, calculates the outflow concentration, and also calculates a new concentration on every day. So you can see here the inflow concentration on day 1 is 4. The outflow concentration is 0 because there's no outflow. But then, as time goes on, the outflow concentration, the concentration in the wetland as well, which is the same as the outflow concentration, that becomes non-zero and starts to follow the concentration that's given for the inflow. But of course there's attenuation that's going on between the inflow and the outflow. The model calculates mass balances to make sure that the calculations are accurate, and those are reported in this little table over here that I talked about before. So the mass balances are conducted so that you can calculate how accurate the results are. All right, so that's an explanation of how this works. I'm certain that you'll have questions about some of the detailed calculations. I've asked you to do the calculations for day 173, and so you'll need to go into the spreadsheet down to day 173, which will be down here. You can see for the the flow routing table, you've got a whole bunch of numbers here that you'll need to verify. And then this is the chemistry section. For the chemistry section, you'll need to verify that those calculations are correct as well. I've specified as to which calculations I want you to do. And then also for the head loss section on day 173, you'll want to verify the head loss calculations too. But you only need to do it for day 173, so the amount of effort is quite small. Designing the wetland shouldn't take you very long. Once you get these parameters in here, you just have to modify the length and width characteristics to keep it within the constraints that are given, and then you can yeah, do the check the results to verify for day 173, and then of course create your plots and your report. And with that, I'll complete this video.